Hi again. So today we'll be looking at learning unit number 12, which is impulse and momentum. So here I've just got the plan for today. It's a short section. So we will start with impulse momentum theorem. But before we do that, it would be nice to define what is impulse and what is momentum. And then we'll use that theorem. Or derive it, and then we'll look at the principle of conservation of linear momentum, and then after that we'll just study collisions both in 1 and 2 dimensions, and then we'll go straight to so some questions from the study guide. Okay, so from the study guide, this is on pages 53, 54 and 55. So page 53, 54 and 55. Okay, so this is learning unit 12. Okay, so what are we studying? As I've said already, it's impulse and momentum. Okay, so what is momentum? So we will study what is called linear momentum. There's angular momentum as well, so which we don't study. So momentum. So by definition, linear momentum, actually we use P. So the symbol P, it's a vector, so we need the arrow on top. It's just the mass times the velocity. So that's the definition. We have already studied velocity, and we know velocity is a vector. Momentum is just velocity multiplied by mass, and it's measured in kilograms, so that's the mass unit, and then meters per second. Okay, so that's the unit for linear momentum. So what is this thing? So remember that if you've got a block and it's moving, say, in that direction, with some speed v, the speed was something like 20 meters per second. So that's how fast the thing was moving. Now with momentum, so we just need to multiply the speed by m, where m is the mass of the object, and now this vector becomes momentum. Okay, so that's how momentum is, and of course you wouldn't say 20 meters per second, maybe the mass is 5, so we multiply the 5 by 20, so that the new the new vector is 100 kilograms times meters per second. Okay, so that's the definition of momentum, and you can see that even though I did not state it, momentum is in the same direction as velocity. Okay, so of course momentum is a vector, so in this case we need to add the fact that this is east according to this diagram. So your momentum would be 100 kilograms meters per second east. Okay, so and then before so by definition, impulse is given by the force acting on an object times the time at which, so how much time the force is in contact with an object. So these are mainly forces to stop an object from moving or to accelerate an object. So for example, if you have a tennis ball and it goes and it bounces, so it falls free fall, bounces off a surface, so say this is h1, and after bouncing, say it reaches a new height h2, which is then when the tennis ball was in contact, it experienced a force from the floor, and it would take some time t to lose contact with the floor. So then the momentum, or the impulse, sorry, is the F times t. Okay, so from Newton's second law, we have learned that F is equals to ma. So if F is equals to ma, what do we know? We know that acceleration is the rate of change in velocity. So now, if I group, so rate of change in velocity, if I now group the mass with the velocity, that's our definition of momentum, right? So I can just write F is equals to, because this is a change, I must also have a change, and then mv is just momentum. So then it's change in momentum over change in time, which is equal to the force. And you can see from here that the change in momentum will then be equal to the force times the change in time. Okay, so we called this thing impulse, and delta P is nothing but momentum. So this is known as the impulse momentum theorem. So this is the impulse momentum theorem. Okay, it tells us that change in momentum is equal to, or is due to the change, the applied force times the time at which the object is in contact with the surface in that case, or with the force. Okay, so that's the impulse momentum theorem. So if I can just show you the summary. So the summary, we said linear momentum is P, and it's a vector, so it has an arrow. And we said P is equals to mass times velocity. So it's velocity multiplied by mass. We know velocity is a vector, and the unit is kilogram meters per second. And you can see that there's no negative sign in front of the equation. So momentum is in the same direction as velocity. And then from Newton's second law, we know that the applied force, or the net force, is the mass times acceleration. But acceleration is change in velocity over time. But we just said now that mv is momentum. So mv would be momentum, but we are studying a change. So then this would be change in momentum over change in time. If you multiply by the delta t, you get delta p is f times delta t. And this is the definition of impulse. And this side is the momentum. So we call this equation the impulse momentum theorem. And notice that there are two units of measurement that we have. So either Newton times second, or you use kilogram meter per second. Both of them are correct. So the Newton second comes from the force times the time, and the kilogram meter per second comes from the momentum side. Okay, so in our plan, we have just covered section 7.1. So now we are interested in the principle of conservation of linear momentum, and let's look at that. So we need a new page. So now we are studying the principle of conservation of linear momentum. Okay, so what does this principle tell us? It tells us that momentum, so for an isolated system, the total momentum is constant. Okay, so it's sometimes they use the word conserved. It's the same as constant. Okay, so that means if I have momentum at some time t1, later on at some time t2, so the momentum before was just p, after some time I must still have p, so the momentum doesn't change, okay, even though the time changed. So that's the conservation of momentum. But how do we write the equation? So we say momentum before, so I'll use a small b as a subscript, equals the momentum after. And this is a general rule, so it's always true. Okay, so how do we use this equation? If, say, for example, you've got two particles, the momentum before is the momentum of particle 1, which is the mass times velocity of particle 1, plus the momentum of particle 2, so the mass times the velocity of particle 2, and after it will be the momentum of particle 1, velocity of particle 1. Later on I'm going to use a prime just to differentiate this speed, this velocity from that, and then the momentum of particle 2 times the velocity, the mass of particle 2 times the velocity of particle 2. So that's how you would use the conservation of momentum, and that's this equation. Okay, so remember that vectors in general have an x and a y component, so that would be the x component and that would be the y component, so for the vector v. So then so let's call this vx and let's call that vy. So if v can be broken down into y and x, and we have conservation of momentum, so then we learn that we have momentum in both the x and the y being conserved. So we have p before in the x direction must equal the momentum after in the x direction, and then momentum before in the y direction must equal momentum after in the y direction. So what I've just written here is still conservation of momentum, but now it's in 2 dimensions. Okay, this here was in 1 dimension. Okay, so now that we have the conservation of momentum, now let's have an example. So an example would be something like, say you are playing pool with your friends. So remember that pool has 6 holes, so 1, 2, 3, 4, 5, 6. Okay, so there's a line where you can't, so where you place your white ball, say that's your white ball, and then over here you've got another ball, say it's the black ball, you're playing against your friend and you're trying to score the black ball. So initially the black ball is stationary, so it's not moving. What that means is the speed v0 of the black ball is equals to 0. The white ball, now you hit the white ball towards the black ball and you want, say you want to score the black ball in this hole. So you've bet with your friends that you are good enough and you can cut this ball so that it goes there. So before the speed of the white ball is v0, and as a velocity I need an arrow, so say that's the case. And then if we are told that after hitting the ball, so remember, actually let's draw a bigger table. Okay, so after playing, what you find, so there's our 6 holes, there's our line that we can cross. After playing, this was the original direction of motion for the white ball. The black ball does indeed, I drew it as blue, so let's be consistent. So if the black ball now does actually go in, but unfortunately for your friend, the white ball also goes in. So if this angle here is 45 degrees and this one is 45 degrees, with respect to the original direction of motion, the question then is what is the total speed? So what is the speed v2? So let's call this white ball 2, the black ball 1. So that's 1, that's 2. And we want to know also what is v1. Okay, so let's assume, so you are told that the mass of the white ball is m and the mass of the black ball is m. So both have masses m. So then how do we study this collision? Remember that we have conservation of momentum in the x direction and in the y direction. Okay, but now which way is the x direction and which way is the y direction? That is up to us. And my advice to you is, when you study problems like this, always choose the direction of motion initially as your x-axis. Okay, so if our x-axis is over here, so that's x, then y has to be perpendicular, so that's y. So even here, that's x and that is y. So now momentum before in the x direction equals momentum after. Actually, it's smarter to start with the y in this case. You will see shortly why. So momentum before in the y direction equals momentum after in the y direction. Okay, so why did I say it's easier to start with the y? Because initially we don't have any y momenta, and afterwards we only have y momenta opposing each other. Okay, whereas initially here we have x momenta, and after we have y momenta. So there's 3 terms here, there's 2 terms there. So it's easier to work with this one. Momentum before is the mass of ball 1, which is m, that's the black ball, and the speed is 0, so it's just 0, and then plus for the white ball it's m, and then the speed or the velocity is v naught, so times v naught, okay, equals m, and then now the final speed is v1. So just to remind you, it's over here, so v1 for the ball plus m times v2 for the white ball. Okay, so this term is just 0, and then here we still have m. Now we need to substitute the vectors. So v naught is going in the positive x direction initially, so it's just plus v naught. Okay, the plus is the direction, the v naught is the magnitude. So that's the momentum before. This is equal to m, and remember that here we are looking at the x, so that's the x component, that's the x component, that's the x component. The x component of v1 is over here, so that's the x component of v1, and that's at an angle of 45 degrees. It's the cos of 45. So then I'll have plus, because it's going towards the positive x direction, it's plus v1. Wait, we're looking at y, so guys, that's y, that's y, that's y. So it's actually going up, so plus v1, and then it's going to be sine 45. Okay, so just make sure we are looking at the y conservation of momentum component. So then we for ball 1 it's going up, and we said up is positive for y, so that's why I have a plus there, and then plus this plus is this plus over here. Then I've got the mass of the white ball and multiplied by, now the y component is pointed down, which is opposite the positive, so that's negative v2, and it's also sine 45. Okay, so now we can okay, so we were looking at the y, so this term over here um, should be 0 because we don't have a y component for the initial speed. The initial speed is only in the x direction, so that term shouldn't be there, it should be 0. Okay, so my mistake, apologies. So this term is just 0 because we are looking at y. So what we learn is 0 is equals to this term plus this term. Okay, so now I'm going to take the negative term to the other side so that it becomes positive. Then it becomes mv2 sine 45 equals mv1 sine 45. Okay, and then now you can see that the m's cancel, the sine 45 cancels. So we learn that v1 equals v2. So that's our first equation. Okay, and then to get the second equation, we use conservation of momentum in the x axis, in the x direction. So momentum before in the x equals momentum after in the x. Before it's the for ball number 1, it's stationary, so the momentum before is 0, it's not moving. And then for ball number 2, it's the m times v naught, and it's a positive because it's going towards the positive x-axis, so it's plus m v naught. After, for ball number 1, which is the black ball, it's positive, so it's m, then the speed is positive v, remember it's v1, so v1, now it's cos 45 degrees, okay, and then plus for the second ball, the mass is m, and the speed is also positive in the positive direction, so it's plus v2, and it's also cos 45. Okay, so if you check the cancel, remember that v1 is v2, so substitute v1 over there. What we learn is on the left hand side we just have v naught over here equals, and then here it's v1, and then this is also v1, so it's the same term twice, so I just get twice v1 times cos 45. So in the end our solution is v1 is equals to, so I have to divide by 2 and the cos 45. Cos 45 is square root 2 over 2. So this 2 cancels that 2, so I'm just left with square root 2. So v1 is equals to, I have to divide by square root 2. It's just 1 over square root 2 times v naught. Okay, so that's our final solution. So v1 is 1 over square root 2 times v naught, and most of the cases v naught is given, but we said v1 is v2, so which is equals to v2, so we have both v1 and v2, and that solves our problem. So how would you quote the final answer? So remember that v1 is a vector, so it will have the magnitude 1 over root 2 times whatever v naught is. Maybe v naught is 10 meters per second, then you substitute 10 meters per second here. And then the direction, if you check at your diagram, it's according to this diagram, it's 45 degrees north. So remember this is east, that's north, so north of east. Okay, so that is how we solve problems for 2 dimensions. Okay, so we are actually done with the material. We started off and we defined impulse, and we said impulse is force times, so it's applied force to change momentum multiplied by t. Then we said momentum is m times v, and we had a momentum impulse theorem, which is over here. So that was delta p is f delta t, and we said that's the units that we use, and it came from Newton's second law. And then after that, we studied the principle of conservation of linear momentum, which tells us that if we have an isolated system, the momentum before equals the momentum after. You might be wondering, what is an isolated system and when is this true or false? So for example, if I have a ball floating in space, that's an isolated system. If I have two balls moving in space, that's also an isolated system. If I have a block on a surface, the isolated system, so the block is moving in some direction, is the whole system. So isolated system in this case would be the block plus the floor. Okay, so if there's friction on the floor, the block will lose some energy to the floor, and we have studied this. This is work done. The floor will then heat up, so that means the energy was transferred from the block to the floor. So as a system combined, the block and the floor would be an isolated system, whereas the block alone is not an isolated system. Okay, so the block alone is not an isolated system. So that's what I mean by isolated. And then we studied collisions in one dimension, and we studied collisions in two dimensions. And here we used an example of the pool table, someone playing the black ball. And then there's two more things that we need to discuss, which are part of the syllabus. So those two more things are the following. So there is something called an elastic collision, and we have an inelastic collision. Okay, elastic collision, all this means is the following. It means the following two things are true. So elastic collision, the kinetic energy is conserved. So kinetic energy before equals kinetic energy after. So, and this will depend on the number of particles, but in most cases you would have two. So if you have two particles, the kinetic energy before is 1/2 the mass of particle 1 multiplied by the initial speed of particle 1 squared plus 1/2 the mass of particle 2, the initial speed of particle 2 squared, and we said this is equal to the kinetic energy after, which is 1/2 the mass of particle 1 times the speed of particle 2, so that's the final particle 1 squared, that's the final, plus 1/2 mass of particle 2 times the speed of particle 2 squared. Okay, so that's the first thing that you have in an elastic collision. We have the fact that kinetic energy is conserved. Okay, and of course, so that's the condition for an elastic collision. Of course, we said conservation of momentum is always true, so we'll just add the fact that momentum before equals momentum after. So here we have m1, the initial speed of, the initial velocity of particle 1 plus mass 2 initial velocity of particle 2 equals, that's the initial, so equals m2 final of number 2 plus the mass m1 times the final velocity of particle 1. So using these two in conjunction, you can then solve the two equations simultaneously to find the final speeds v1 and v2. Okay, so that's an elastic collision. And then what is an inelastic collision? Inelastic collision means the two particles move together after colliding. Okay, so assume we had a strange pool game or table. That would mean in our example that we did earlier, you have the white ball, there is the black ball. It hits, so the white ball hits the black ball, and then afterwards what you have is both the white and the black move together to whatever hole you have. So here, of course, you would win by not scoring, because if you score the black ball and the white ball, you lose. So your aim here would be not to score. Okay, so the other thing is that, remember that we said for elastic the kinetic energy was conserved. So here obviously the kinetic energy is not conserved. So Ek before is not equals to Ek after. Okay, so how do we do calculations here? So before, remember momentum is always conserved. So momentum before is momentum after. So before, say that's M1, that's M2. Then here they are moving together, so you'll have mass 1 plus mass 2. So what you learn, actually this diagram is wrong. It should be moving in the x direction to conserve the y momentum, because before there was no y momentum, but it's just for the purpose of showing you how it moves. So here we will have the mass 1 times the initial velocity of particle 1 plus mass 2 times the initial velocity of particle 2. This is equal to, remember afterwards they stick together, so that means the total mass m1 plus m2 will then have a speed v. Okay, so that's the key. The key is afterwards these two would then move together. Okay, so now we have completed the section. Now we want to study some examples. Okay, so the examples I'm going to look at are from the study guide. So if you can now go to page 54. Okay, so page 54 of your study guide. In particular, we're going to start with question 1. So question 1 is, I'm looking at the tutorial questions. So can a single object have kinetic energy but no momentum? Explain your answer. Okay, so how do we answer a question like this? So we are looking at page 54, the tutorial problems. So these are tutorials, and now we are looking at number 1. Okay, so number 1 is asking, can a single object have kinetic energy but no momentum? So if I have one particle, can it have kinetic energy but no momentum? So momentum is 0. How did we define momentum? We said momentum equals mass times velocity. Kinetic energy was 1/2 mv squared. So v is the speed of the ball. So if the ball has speed v, that means it has velocity v, which means if I multiply the velocity, it has okay. So if I multiply the velocity by m, that means it has momentum. So the answer is no. It can't have kinetic energy and no momentum. Okay, so having kinetic energy implies that you have momentum. Okay, because both depend. So kinetic energy depends on speed, momentum is velocity. So having speed means you have velocity, which means you have momentum. So this is implied. Okay, so that's number 1. And then now let's look at number 2. So same page, number 2. Okay, so I should have swapped. So just to remind you, so we said if an object has kinetic energy, it means it has speed. What that means is if it has speed, it has 1/2 mv squared, but having speed implies you have velocity. Having velocity, if I just multiply by the mass, now I have momentum. So you can't have an object having kinetic energy and zero momentum. So having kinetic energy implies you have momentum, because kinetic energy depends on speed and momentum depends on velocity. So having speed, you have velocity, which means you have momentum. Okay, so that's number one. And then now number two. So let's read the number two. So number two says, can a system of two or more objects have a total kinetic energy that is non-zero, but a total momentum that is zero? And explain your answer. Okay, so here